attraction? Gravity, because the Earth attracts everything, but it doesn't fall. So there's a third force, buoyant force, three forces. Now I can hit it. That would be the fourth force, yeah, contact force. And I could use some fluid dynamics. That would be pressure. But now I want to try. I'll explain why. I'm just trying. I want to try to do something different. Too much air. Sometimes it helps. Okay. Did you see it? What did you see? What did you see? This too moist. What did you see? What was happening with the balloon when I was moving my bat away from it very slowly from very close direction? From very close, let's try this one. This is drier. Okay. So last time, maybe here there's not too much flow, airflow. And if it's very, very still, and let's try silk. Okay, you have to see, yeah, the attraction between this balloon and this bat. The bat definitely attracts it, even when it doesn't touch it. So now you can answer this question. What force was acting on this balloon from this bat? It did its job, it's free now. Naturally, I expect that you would eliminate gravity, because gravitational attraction requires a lot of mass in order to be measurable. No elastic. You don't see any strings or springs between the bat and the balloon. They don't touch each other. That's not a buoyant force. So there are only two questions, answers, but the least reasonable, logical would be the last one. So the right answer is none of the above. And in physics, well, actually, let's try one more time. In physics, when we observe something which might be important, let's see if we can, oh, yeah, yeah. See, it is relatively strong, stronger than gravity acting on these peanuts. So it might be important, and of course, it has been important. If something is important, first we name it, and then we study its properties. And this type of the force has a name, electric force, or electrostatical force. And this topic has a name, electrostatics, because we talk about objects which experience or can produce that type of force, but technically normally not moving. And this experiment shows you how to generate a force like that. We have to use two objects to bring in contact, in physical, mechanical contact. Why? Well, now we know why. People didn't know when they started to study this force, but now we know because inside everything we have special objects. We call them molecules, but inside molecules we have special objects. We call them atoms, and inside atoms we have special objects. We call them electrons and a nucleus. And nucleus also composed of other atoms, but we should stop at electrons and a nucleus, because those particles, tiny particles, invisible particles for the naked eye, but they have very special property which we call charge. And that property tells us if you have two objects with that property close to each other, they attract or repel each other. And let's see if I all right. Let's see if I can repeat some experiments. Unfortunately, in the summer, all these experiments might not work due to high humidity, because molecules of water, when they stick to, well, objects or cloth, they ruin this property. So when you're going to be doing lab 1 on Thursday or on Friday, depending on the weather, you might be very happy or very frustrated. Because depending on the weather, things might work pretty well for you or not at all. So I'm not sure. This device has a name, an electroscope. Scope means we're looking at it. And this device demonstrates the absence or the presence of electric charge. Nothing, not charged. But here we can see some change in the state of this device. Move away, neutral again, bring it close, and I don't touch it. But something happens. So, okay, we got to explain this experiment when we will. What's going to happen if I try to actually kind of scratch off something a little? Yeah, we can see. Maybe I can try add some more. Works. This is also like a simple electroscope. So we can see repulsion. And by the way, we can see that that repulsion, the strength of that repulsion depends on other features of this experiment. Distance, for example, between the bat and the plate of the electroscope. So something to explain. Now, let's see what else can we do. First of all, I always want to check if an object is charged or not. Nothing, so it has no charge. Okay. Okay, so this bat now has a charge. Oops. I see repulsion. Well, that only can happen if this plastic also has some charge. Maybe small, so small we cannot actually see it, but the repulsion can only happen when both objects have a charge. Okay, I'll try a different one. Oops, this one. Don't see anything. So I did the check. And I used the bat because it is made of very good plastic. It holds the charge very good. Now let's see. Okay, now we can see attraction. Now, first of all, this rod has no charge. This does have a charge, and we can see attraction. Okay, little charge. What do we see if they both have a charge? Now we can see repulsion. So these type of experiments show us that depending on various features of cloth or materials, two objects might only repel or attract each other. If they don't interact at all, that means they're both neutral. Neither have a charge. Now, if they attract each other, that means they should be different. And people could have called them black and red, for example, or sweet and sour, but they call it plus and minus, positive and negative. And experiments had shown that like charges always repel each other. Negative and negative repel, positive and positive repel, but opposite charges always attract each other. And if we look inside an atom, electrons, those tiny particles which orbit the nucleus, have or carry a negative charge, and the nucleus carries a positive charge, so they attract each other, but electrons don't fly away because the attraction holds them. We could make electrons move away. How? By mechanically moving them away. That's what we're doing. When I put the piece of Thor close with the plastic and I start rubbing Thor against the plastic, there's mechanical interaction. And because of that interaction, some of the electrons getting moved from fur on this plastic. And initially, before I rubbed them together, both objects were neutral. And this word neutral means total net charge of the whole thing is zero. And that means the number of electrons inside this bat is equal to the number of, well, those tiny particles, protons. And you remember from chemistry, a proton is inside the nucleus. So if we have exactly the same number of positive charges and negative charges, they cancel each other out, total charge is zero. Every single object in the universe in its normal state is neutral. We have to do something about it to break it. And what do we do? Well, mechanical interaction. In that case, well, theoretically, when we have two objects interacting, we have only two options. Option number one, electrons run from object number one to object number two, or electrons run in other direction. Well, it's just a fact from many, many previous experiments. If we have a fur and plastic, electrons run from fur on plastic. So fur loses some electrons, that piece of plastic gains some electrons, and they both become charged, not neutral anymore. So the magnitude of the force more coffee. The magnitude of the force between two charges depends on the magnitude of each charge and the distance between those charges. And the expression has been proved from experiments by physicist Coulomb. So that's why we call it Coulomb's law. And the structure of this law is very, very similar to the Newton's law of gravity. That's why many people like calling mass as a gravitational charge, because this is electric charge. So you have two objects, each has certain electric charge, and the force is proportional to the product and inversely proportional to distance squared. We increase the distance, the force decreases. We bring them closer, the force increases. How does it point? That doesn't depend on the magnitudes, that depends on, and that term is polarity. They have polarity, positive or negative. Negative polarity. Two negatives repel each other. Negative, positive attract each other. That's how we figure out the direction of the force. And if we know the magnitude and direction for two charges, of course we can calculate net force acting on a charge from many other charges, and we will do. This is the magnitude of so-called elementary charge. Well, what does it mean, elementary? It means we don't know so far the charge less than that the smallest portion of a charge in the universe. And all other charge is measured in terms of this portion. It could be only one elementary charge, or two, or 100, or 25 billion. That's it. It depends on how many electrons or protons put together. This is the charge of an electron, negative 1.6 times 10 to the negative 19, and this is a unit for a charge using international system of units, a Coulomb. For a proton, the magnitude is the same, but the proton is positive. So if you have a hydrogen atom, one proton, one electron, the total charge is 0. If I have a helium atom, two protons inside, well, two neutrons as well, but they're neutral, and two electrons, the total charge is 0. For every atom, the total charge is 0 until we make it an ion. And ionization means we may add an extra electron or remove an electron. In that case, the total charge of the ion is not 0 anymore. So again, you don't know what to say yet because you don't see the experiment. But you can prepare your Weber sign. I need a space. I need a big ball. I need this. Then I want to check if it actually works today. You know what? All right. It does work. Now I used There are two options. Number one, I forget to bring a ping pong ball. Number two, someone stole it. Well, doesn't matter. That's the experiment. A big ball, small ball. Watch closely. So now you can enter your question. Your answer. Now you can enter your answer. Where's everything? Yeah, this building has ghosts. Still works. Of course, physics always works. Well, what is the right answer? Mass matters. Mass does matter. We know, first of all, because of the Newton's second law. The acceleration is inversely proportional to the mass. But this experiment represents the model of protons and electrons, or even something more heavier than a proton, the nucleus in electrons. Each proton is about 2,000 times heavier than a single electron. But if we have a nucleus which has several protons and several neutrons, each nucleus will be 10, maybe 1,000 times heavier, which means they just can't be moved. Anytime when we bring two objects into contact, only electrons can move one way or another, only electrons. And every single experiment which you saw and we will see and we will be trying to do in the lab has to be explained in terms of electrons moving one way or another. That's it. So it's all about electrons. And of course electrons, because they all negative, they always repel each other, which means as soon as they have an option to run away from each other, they use that option. So they try to have as much space between each other as possible. And this simple principle describes all experiments with electrostatics. And of course, we cannot destroy or create particles. So the total amount of particles inside an insulated system always remains the same. So when I rub the piece of fur against plastic, if this piece of fur loses 100 electrons, that means this piece of plastic gains 100 of electrons. That's it. We cannot create or destroy those particles. And this law, of course, has a name, the law of conservation. In this particular interpretation, a law of conservation of electric charge, or in general, it's a law of conservation of electric energy. Anyway, just to review our understanding, please answer this question. We have an object, for example, this red ball, and we know, doesn't matter how, doesn't matter why, but we know that it is missing some electrons compared to its neutral state. So what can you say about the charge of this object? And of course, if it is a charge, the possible answers are it's positive, it's negative, or it's zero. Only three options. If it has a deficiency of electrons, the charge just can't be zero, so it has to be positive or negative. Now, what does deficiency mean? That's a linguistic question. It means we have taken some electrons off it. So if it was neutral, means the positive and negative charge were balanced, and now we're decreasing negative charge by removing electrons. What's left? Positive. That's it. That is the type of reasoning which you should use when you choose the answer yes, it should be positively charged. Now, sometimes we want to bring the object back to its neutral state. The best way to do that is using a conductive paper or foil. We can't, please remember that, because people tried. We cannot charge an object using aluminum foil. To charge an object, we should use something like a fur, wool, silk. Foil is to make it neutral again. So let's say this ball was positively charged, so was positive, but that means this ball was missing some electrons. So what's happening? Now that ball gains those missing electrons from this aluminum foil. What is the difference between aluminum and plastic? Well, inside aluminum or any other metal, electrons might be moved very, very easily. We don't have to apply a strong force for that. Inside plastic, we also can move electrons, but that would require much stronger force. We would basically break it. Let's see. So this is another very good plastic. So I have a soda can, and I want to charge this. That's better. This flamingo. Okay. See, I don't touch it. But clearly there is a force of attraction acting from flamingo this can. Now, what is the difference between this can and the second object is 2x4. 2x4 is a piece of wood like this. And the difference is, as we just said, the aluminum can is made of conductive material. Electrons can be easily moved. And this is, well, we call it a dielectric, and we're going to talk about conductors and dielectrics. It's also wet. Okay. Let's see if I can do anything with this. Stop. See? Power. Maybe bat will work better. Yep. Again, attraction. Now, these two objects are neutral. I didn't charge them. I didn't rub them with anything. But no matter if the object is conductor or dielectric, we observe a strong force between the charged bat and that object. Now we have to look inside. We need to start looking inside, seeing what is happening. So let's say we have a can. What does it have inside? Well, it has negative and positive charges in the same amount, the same number. So 666, 666. That's the first state. Nothing is acting on it, just at rest. Now what's going to happen if I have this can? Okay, I'm just going to do a rectangle. And I bring a bat close to it. I know the bat carries some charge, and I know from experience it has extra electrons, so it has a negative charge on it. But electrons inside the can now start feeling, interacting with electrons on the bat. How? They have to repel each other. Electrons in the bat can't really move because it's made of plastic. It's not a conductor. But electrons in the can can. And because they being repelled, so more electrons being collected on the farther side from the bat. Which means that we observe the separation of charges inside this can. The total charge still remains 0, but the charge distribution has changed. Now we have an extra positive charge closer to the bat, and because of that, we observe attraction. There is, of course, some repulsion, but because the distance between positive charges and the bat is less than distance between negative charges and the bat, the force of attraction is stronger than the force of repulsion. So there is a net force which we observe. This is just an example of a reasoning. How do we explain the phenomenon based on the fact that only electrons can move and they repel each other? Now, slightly more complicated actually case when we attract a dielectric. As we said, in a dielectric, electrons just cannot easily move. They cannot move away from it. But something still happens, something very important. So if this is a piece of wood, and now I'm going to start from the case when we bring a bat very close to it. What's happening? Now you have to use your imagination. Let's say each atom or molecule is neutral, maybe it's larger, almost spherical. Electrons are outside, the nucleus inside. But when we start bringing the strong negative charge close to it, that should affect electrons. They don't move away across the wood, but inside that atom or inside that molecule, we observe some distortion. Okay, that's the nucleus. But now electrons travel like this, a little bit away. So each individual molecule becomes, the name for this phenomenon is polarized. So it was something like this, a positive charge with electrons around it, and now it has become polarized, something like this, with electrons shifted to like this. They still orbit the same nucleus, but the trajectory is distorted. And now what's happening again, this happens to all molecules, to all atoms. Here, close to the bat, we will see a layer, very thin, tiny layer of a positive charge, and here on the opposite side, we will see a layer, a very thin layer of a negative charge. That's important because we will use this picture in the future to describe the properties of electric field inside the dielectric. And what is electric field? We don't know yet, so we have to talk about it later. But we will have to talk about it later using this experiment, this picture. Inside, of course, we have well, layers which compensate each other. So inside there is nothing interesting, but on the outside of a dielectric, we have two opposite layers of charges. And again, now the force of attraction will be stronger than the force of repulsion. Same reason. Distance matters. Distance different. When we bring charges closer, that increases the strength of the force. And again, we can see attraction. The most important take from this is when we see attraction, it does not necessarily mean both objects are charged. Attraction might mean two things. Number one, they have opposite polarity, plus and minus. Or number two, one is charged, second is neutral. But we say inside that neutral object, we induce some new charge distribution. So it's induced attraction. Repulsion is much easier. If we see two objects repel each other, that only means they have the same polarity. If two objects repel each other, they must be both positive or both negative. That's it. Because, again, a neutral and a charged object only attract each other. Well, these are pictures which you can understand. You couldn't understand these, of course. So how do we attract insulator? How do we attract a conductor? Now, I demonstrated to you how to charge an electroscope by scratching a charge of a charged object. We can see a charge, okay. Now we can physically let electrons move from the bat, just a little. Let's try this one. There's a second, so this is a charging by contact. Let's try this one. So two objects are brought into a contact, better. How do I discharge it? Well, I can use my hand, for example. I just scratching off electrons. There's a second way, sometimes more reliable, a little bit trickier, but more reliable. Let's see if I can do it now. So I don't touch the plate of the electroscope. Instead, I touch the electroscope by my finger. I induced the charge. This is called charging by induction. Now let's explain what is happening in both situations. Well, the first situation is easy. Yeah? We have an electroscope. It's initially neutral. And then we're just adding, I don't like red, electrons are blue. I'm just adding electrons to an initially neutral piece of aluminum. So what's happening? They repel each other, which means they start running down. And the moving arm of the electroscope is also made of aluminum. So it also gains some electrons. And now at the bottom of this electroscope, we have two negative objects repelling each other. That's what we observe. Now, a different experiment has two stages. Yeah? Stage number one. I hold a negatively charged object close to the plate. What does it do to electrons in the plate? It repels those electrons. So those electrons now starting moving down by being repelled. So we have some extra electrons collected here at the bottom. And we saw the deflection because they repel each other, there is a force. But now I touched it with my finger. So what happened if I touch it with my finger? That was stage number one. Stage number two. By touching it with my finger, I give electrons extra room to run. So now, some electrons being moved, because they repel each other, from the electroscope on my finger, and then I remove the finger. So if electroscope was initially neutral, and now I removed some electrons, what's left? deficiency of electrons make this electroscope positively charged. And again, we observe the repulsion. I used the same bat, the same negatively charged object, and we can see if I charge the second object by bringing them in contact, the second object carries the same charge as the initial object. But if I charge it by induction, the second object now charges opposite charge. And well, this is what we can use when we need to know what to do if I want to make electroscope positively charged or negatively charged. These are my options. Now, how do we know when the bat or a rod becomes positively charged or negatively charged? Well, it's been studied for hundreds of years. Now we know if we take two pieces, bring together, one becomes positively charged, second becomes negatively charged. And there's a table which tells us which will be which. So if you use wool and PVC will be negatively charged and the wool will be positively charged. So we just have to follow this chart. Of course, in physics we have other means, but they're more complicated. Well, so one more experiment. We've done it, but just want to talk about it. So I want to try to charge it by induction, because when it's very humid, it's more reliable. Okay. Now let's see. Okay, this seems absolutely neutral. The charge is leaking away very quickly. That's another issue. We have to be very, very quick. When it's a dry weather, the charge might stay for a long period of time. But when it's what's going to happen if it's charged? It's actually now positively charged, and I bring a negatively charged bat close to it. We can see how it changes. Why? Well, because if it's positively charged and it's negatively charged, when I bring it close, electrons in the plate being repelled and move down, and they start compensating the positive charge, so less charge at the bottom, less force. And similar experiments, of course, can be done with negatively charged electroscope, a neutral object, a conductive object, and we always can figure out what might happen with the angle. The angle, of course, also depends on the force of gravity. Without force of gravity, repulsion would make it moving arm move away as far as possible. So we will solve a problem when two forces, gravity and electrostatic, act together, but not on a complicated system like this, just on a ball, on a string. Well, okay, a conclusion. So we said that, we said this. And this is an explanation, how can we charge by induction. And this is the conclusion. Every experiment like that is based on these simple principles. Number one, we cannot destroy or create any charge. The total number is always conserved. Electrons always repel each other. Protons never move. Only electrons can move. And the total charge always is equal to, well, the number of extra or missing electrons times 1.6 times 10 to the negative 19th. That's it. Any questions? This is just a summary of everything I just said. We can have positive charges, negative charges. And if we have many of them put together, the result also might be positive, negative, or zero. And this equation tells us how to calculate the number of missing electrons or number of extra electrons if we know the charge of an object. So we just have to divide the charge by the magnitude of the elementary charge. Question, please. So I do have two spheres like that, and I can rub each sphere with certain material, one with fur, second with silk. Then I can take them, touch, even hold together for a certain period. And the question is, what should happen with the charge? What do you think should happen with it? So today is not really a humid day. And as you could see, the experiments worked more or less. So if on Friday or on Thursday the weather will be similar, you should be able to do at least some of the experiments. If it will be drier, you should be able to do more. If it will be more humid, you will become a physicist. Very frustrated. So let's see what you say. We charge two plastic spheres, bring together, and move them apart again. Move them apart again. How does it affect the charge on each sphere? Question number 6. Survey says, move, 5, 6. So 73% of students says the charge will change, and 24%, the minority, said it won't. And this is again a demonstration of the very important fact, which is what? Democracy doesn't work in physics. Democracy is a dictatorship by the laws. The key word, there's one word in the whole sentence which is much more important than all other words. Can you find that word? No. No. Plastic. What does it tell us? In plastic, charges don't move. That's what is the difference between a plastic, which is insulator or dielectric, and an aluminum or steel or copper, which is a metal or conductor. So nothing would really change. Of course, if we want to make a change, we need two conductive objects. We could charge both and then touch, and in that case, electrons can easily move. And in that case, the charge will change. So I tricked you, which is a good thing. You remember now. So now let's just solve a specific problem. Metallic spheres, conductive spheres, identical spheres, both have been charged. We can calculate the charge because we know conversion factor. For example, the charge of the sphere on the left will be equal to 7 times 1.6 times 10 to the negative 19th times 10 to the 22nd. This is how we read it. 7 times Q. Q represents the product of the elementary charge and a given power, and that's the elementary charge, coulombs. We don't have to know this actual value. You know, it's not important for this problem, at least for now. QB will be equal to -3 times same coefficient, 1.6 times 10 to the -19th times 10 to the 22nd coulombs. This is just a fact that we know the initial charges. That's it. Now, in physics, every question or every problem is based only on a definition or a law. There's nothing else in physics, definitions and laws. This problem is based on the application of a law, which is not this one, not that, not that. Essentially, could have been energy, but that doesn't really help because everything basically converted to energy, mc squared. So, not this, this. We have to apply the law of conservation of charge. And what does it say? Total charge of a system remains the same, no matter what, if it's an insulated system. That's it. So first, we'll need to search for the law or definition or combination of laws and definition, which we can use to solve this problem. And then we have to apply those laws to solve this problem. So please, you start answering the question number 7. What do you expect to happen to the electrons? How would they move during the period the spheres touch each other? They will move. And I'm going to start from applying the law. So the word conservation says we have to compare two situations, initial and final. The initial situation. So the initial charge of the whole system has to be equal to the initial charge of the sphere A plus the initial charge of the sphere B. And I'm just going to use so far the coefficients. That's the initial charge of sphere A plus, because that's what the law says, add the charges. But the second charge is negative. Now we have to do some mathematics. 7 minus 3, 4. And if you want to ask me, how much is it in coulombs? Well, I know the coefficient. Q represents 1.6 times 10 to the negative 19th times 10 to the 22nd coulombs. That's it. All right. That's not the law yet. That's just a part of the law. Second part of the law, final state. Q final should be equal to what? According to a definition of a total charge, it has to be equal to the sum of the charges of individual parts of the system. This system has two parts. We call them A and B. That should be final charge of a sphere A plus final charge of the sphere B. Nothing else can be done. That's it. Is it a law? Not yet. What does the law say? It says that Q initial has to be equal to Q final. That's what the law of conservation of electrical charge says. That is a statement, mathematical statement of the law. Okay. Before we moving on, question 7. Six, 7, running. 7, we see the 2 now is most popular, and the 2 now is correct. So, but it doesn't mean democracy works in physics, no. And how do we know that? Well, if we look at the charges, of course, this sphere missing some electrons, and this sphere carries some extra electrons. So as long as we let them run, we don't have to actually touch together. We could connect them with a wire, like a copper wire, which is a conductor. And again, in this situation, electrons on the right would be repelling each other, and they would started traveling to the left, being attracted to that positive charge. But this motion can't happen forever. Eventually, it should stop. That's what we call equilibrium. Not thermal equilibrium, not mechanical. Now it's electrical equilibrium. Eventually, the electrical equilibrium will be reached, and eventually each sphere will have a different charge. We call it Q final A, Q final B, but if we add them up together, the total number should be the same as before. That's what the law says. So now we can, this is the strategy. Now we can use that law. So 4 times Q should be equal to Q final A plus Q final B. That's the initial charge of the system. That's the final charge of the system. We have one equation which has 2 unknowns. Mathematically, it should be like 7 equals x plus y. This is a very standard situation when we have to choose between 2 options. The option number 1, we just give up. The option number 2, searching for extra information which could have been used, which haven't been used yet. Where do we search it for? Well, normally in the text of the problem. That's where all the information should be provided. So this is the text of this problem. 2 identical charged metallic spheres touched each other. We have to find something important which we didn't use yet. Please tell me. Yes. Exactly. Have you been taking this course before? Have you been taking PY105 with me before? I remember you, which is a good thing for me. I still remember things. So, I remember faces. I don't expect me to remember your names. So, that's absolutely correct statement. Those spheres are identical, which means in the end, when allowed, they should store the exact amount of charge, identical charge. That's an additional statement which has nothing to do to the law. It's a feature of this particular experiment. If we had different spheres, and small and big, this big sphere, of course, could store more charge. But that's not the case. Our case, they store the same charge. How do we Q final A, Q final B? How do we make this statement written mathematically? How do we write it mathematically? They are equal to each other. Now we have two equations and two unknowns. So now it's doable, it's solvable. Let's see. Okay, that's his answer. So first, let's quickly, come on. Let's quickly finish. Although we already know what to do, but let's just do it. So now we have two equations. The equation number one represents the law of conservation of the electric charge. Second equation represents the specific feature of this situation. How do we solve it? For Q should be equal to Q this plus same. What did I do? We call it a substitution. I've replaced one variable with another one which is equal to that. So that's going to be 2 times this. So the final charge for both will be equal to 4 over 2 times Q, or 2 times this factor. Or if we want to, we can calculate it in coulombs using information given to us. That's how many coulombs. 3.2 times 10 to, what is it, 22 minus 19, 3 coulombs. This is actually a very, very large charge. It's very hard in reality to create 1 coulomb of charge because the electric repulsion is so strong, electrons start repelling each other and they just leak away from the surface. And immediately we can calculate on the next table how many electrons actually moved. What do we do? Well, for example, we can calculate how many electrons initially we had on each sphere, let's say sphere A. So initial charge for sphere A was equal to 7 times Q, or 7 times 1.6 10 to the negative 19 times 10 to the 22nd. Now we know that the final charge is this. What is the number of electrons associated with a charge? Well, N E initial was equal to Q A initial over 1, well, elementary charge. Now, good question to ask. This number, does it represent missing electrons or extra electrons? Missing. This sphere is positively charged. This is how many electrons are missing. They've been removed. So that's going to be 1.6 times 10 to the negative 19th is the elementary charge. So if we divide by this, the result is 7 times 10 to the 22nd. What unit should I write? None. The number of electrons has no unit, just a number. Now, final number of electrons on the same sphere is final charge divided by the elementary charge. And that will be equal to 2 times 10 to the 22nd, right? So the change, how many electrons moved, is just the difference. And where did we get those electrons? From sphere B. That sphere lost those electrons to sphere A. Any questions? Well, we are done with charging and discharging. Now we're going to start applying the law to analyze specific situations when charges are interacting. The Bohr model of atom, very important model, describes two charges. One is positive, one is negative. And well, of course, first step is to redraw the picture using our own hand. That's a proton. That's an electron. Of course, in reality, we don't see any trajectory. We're imagining the simplest model, circular motion. And what do we know about circular motion? Everything. That's the right answer. So now, in addition to what we've learned about circular motion, we just have to add one more equation, the Coulomb's law, which describes the magnitude of the fourth force between two charges. How do we calculate it? Well, the magnitude of this force should be equal to the Coulomb's constant. And the Coulomb's constant for the Weber sign should be equal to 8.99 times 10 to the 9th. Just in case. For one of the students, for one of the problem, one question might depend on how accurate the constant is. That's it. But for us, for all our calculations, it's just 9 times 10 to the 9th. So, and we have to use the magnitude of the first charge, magnitude of the second charge, divided by distance squared. So we can actually calculate this number for the proton and electron because everything is given. 9 times 10 to the 9th. I'm not going to calculate the number. I'm just going to plug in numbers. 1.6 times 10 to the negative 19th. That's the charge of a proton. But the elementary charge is equal to the magnitude of the charge of a proton and the magnitude of the charge of an electron. They have the same charge. So we just have to square the elementary charge here, divided by the distance squared. And again, for the Weber sign, you would be using 9.1 times 10 to the negative 31st. But here, I'm just using 9. And that should be squared. And don't forget that when you square things, parentheses must show what you want to square, that the whole thing. That's it. Now you just take a calculator, calculate it, and you get the number in newtons. And now the same force should be equal to mass times acceleration. In this situation, that is centripetal acceleration. And centripetal acceleration is equal to speed squared over the radius. And this is how we can calculate the speed. It has to be equal to force times the radius divided by the mass and square root of that. Oh. The distance is 5 times 10 to the negative 11. That's the distance squared. This is the mass. That's why I said oh. And this is my alarm which says we are done for today. So today I have my office hours, so I'm going to go to the office hour room right after.